That was the magnetic fields with I Wish I Had an Evil Twin. Magnetic fields is what we're studying this week, and if I was an evil twin, if I had an evil twin, it would have blue hair. That is our hat slash wig for this particular presentation. Magnetism is our first lesson where we really deal with 3 dimensions. Before this, we've always just had basically up and down, we call it the Y direction, or right and left, and that's the X direction. But now we also have to go into and out of the page, and so we have to have a way of representing that. So the first thing we do for this unit is talk about what that means. So if we're going to do something that goes into the page, we're going to do a circle, or just a circle with an X in it, or just an X like that. And that's supposed to represent an arrow. So if you took an arrow is going into the page, all you would see is the feathers on the back of it. And so that's why it's an X. And that's also why out of the page is a dot. It's the dot that is the point of the arrow about to stab you in the eye. So that's the way you can remember which one's which. Then in the plane of the page, we're doing the same things we always have. And so then this is a representation of trying to get 3-dimensional drawing where the green line is going in through the red circle. And if we turn it a little bit this way, we get this picture. And so that arrow is going into the page, so we put a circle with an X in it, and the red circle is going around it. But if we turn it the other way, so the circle is basically going around like this, and it's on this top part, it's coming out of the page, and on the bottom part, it's going into the page. So it's going in a big circle, and we can talk about that going in and that coming out as it goes around in its circle that goes like that. So we have to be able to talk about which directions those go, and so from now on, X is in, dots out. Just like with electricity, we had electric field. In magnetism, we have a magnetic field. And in electric field, it showed the way that a positive charge would go, and all of this field shows the way that a north pole would move. And so a north pole is going to be repelled by that side, and a north pole is going to be attracted by that side. So that's why those arrows are going that way. Now, it turns out that every bit of magnetic field that's made is made by a moving charge, and so it always makes a circle. And so that means that on the inside of my magnet, I always have the magnetism going from south to north so that it completes the circle. So outside the magnet, it's always showing the way a north pole would move. Inside, it's going basically the opposite. It's completing the circle to make it always be a circle. Magnetic field is. So this is a quick picture of the fact that any moving charge is what creates magnetic field, and this charge moving in this direction is making a bunch of different circles that come away from it as it's moving. And that's where all magnetism comes from, is from moving electric charge or changing electric field, which we'll talk about when we get to light. But that's the basis for all of it, and then we move on to more than one. More than one charge together becomes current. And so if all of this charge is moving downwards, we get a current going down that way, and so it makes circles. And since more than one's moving, it's continually making new magnetic field that keeps moving outwards. And so we have a bunch of concentric circles like I have up here. And then since it's going all the way up and down the wire, we have those concentric circles everywhere. And so we have them here and here. We could draw more of them out. As long as it's continual charge, we have a lot of magnetic field. And so that means that every circuit that we made in the last chapter, as long as it had current going through it, was creating magnetic field. And so that's why you don't want to put a compass next to an electronic device when you're trying to find north, because the electronic device is making more magnetic field that throws off your compass. We have a nice equation right here for the magnitude of a magnetic field. B, which is my magnetic field variable, is measured in Teslas. And it's equal to mu sub aught, which is a constant. It's related to E sub aught, but it's not quite the same thing. Different units. That times the current, so the more current we have going through, the more magnetic field. That sort of makes sense. And then divided by the distance away from the wire, but change that into circumference because it's going out in concentric circles. So the farther away it gets, the less strong the magnetic field is. And since magnetic field is a vector, because it's got a direction, since it's a vector, we need to find its direction. And if you're doing a circle around a wire, there's only really 2 ways you can go. That way or that way. And when we have 2 different ways to do it, we call it polarity. And since our hands have a polarity of a right hand and a left hand, we actually use our right hand to find the direction that the magnetic field would go for a positive charge. And so we have the electric field, the electric current is going upwards, We take our thumb and we put our thumb in that direction. We curl our fingers around our thumb as if the thumb were the wire itself, and it shows which way the magnetic field goes around. In this case, it goes around in that direction. And if we were doing non-conventional current, conventional current use right-hand rule. If we were using electrons instead, we use our left hand. And you remember we said that conventional current was the same thing, you get the same results. And to prove that, what we do is we know that if a positive charge is moving up in my wire, electrons will be moving down. And in that case, we take our left hand, we go down with our with our current, and our magnetic field still goes around in that direction. The same way it did for positive going up, negative going down gives us the same result. Still a little weird that we're doing it, but you know, get the same result. That's good. And with this electric field, we also sometimes take and we wrap our wire around a piece of metal to make a big magnet. If we do that, our current is going to go up, and then because it's wrapped in this direction, it'll go down. And for this kind of right-hand rule, because they're all adding up together, we can take our fingers and curl them in the direction of, the current, in this case going up and over, and our thumb shows us that the direction of the magnetic field through the center of this magnet goes this way, and it always points towards north and away from south. We're going to do a bunch of examples of this kind and this kind in class. If you don't quite get it now, just be patient and we'll talk about it. They're really kind of easy problems, but we do have to do a little bit of practice before we get it. Because we said every moving charge creates its own magnetic field, if we have a charge moving through an external magnetic field, it's going to make its own magnetic field which interacts with the external one and creates a force on it. And so to get a force on a particle moving through it has to be moving through a magnetic field and it has to be charged. So it has to have a plus or a minus on it and it has to be moving. If it's just sitting still, nothing. Also, if it's going in the same direction as the magnetic field, it won't, because our equation for the magnitude has a sign of theta in it. So if theta sign is 0 or 180, you get no force. So it's only if it's basically at 90 degrees to our force we get to our magnetic field that we get the most force. But our equation says it's Q times V times B. So the bigger the charge, the bigger the force. Faster it's going, the bigger the force, and the bigger magnetic field. And then the last bit is the theta. If, for instance, you have a magnetic field going up and your velocity is going that angle right there, this would be your theta. Really, it says that only the velocity that's at 90 degrees, so you could find that segment of it is making it go in you have a force on it. So because force is a vector, we need to have a direction for it. And we're going to use the right-hand rule again. We're going to use our right hand for all conventional current. We're going to try to use the right hand as much as possible, just because if you try to use both all the time, it gets a little confusing. And since AP uses conventional current, we use the right hand. We take our hand and we put our thumb in the direction of the velocity. The way to remember that is to think like you're hitchhiking a ride with the moving electrons, and so you use your thumb to hitchhike. And you can take your fingers and put them in the direction of the magnetic field with your right hand. You have more than one finger and there's more than one magnetic field line, so that's how you remember that. And when you do that, your palm is going to show you a force, as if you had an arrow coming out the palm of your hand, shows you the force. And if you use your right hand, thumb goes up, your fingers go that way, and your palm shows you the force comes directly out of the screen. And so for your force, you say a circle with a dot. You can even put that circle with a dot on the actual thing and put an F on it and say the force is coming out of the page. If you put a whole bunch of charges together, they make a current. And so we have another force equation for currents. For currents, we do BIL, and it's a sine theta again, and the angle again is between the motion and the magnetic field. In this case, we put a magnet there, and we remember that the magnetic field always goes away from north and towards south outside of the battery. And so we got the magnetic field going that direction. Then we take our right hand and we show that the force comes out of the page. They put it as an arrow going that way. You probably could more accurately do that. Very similar to the velocity one. Your thumb goes in the direction of the current. Your fingers go in the direction of the magnetic field that way. and your palm goes straight out, so your force comes out towards you. Yep. Just a quick picture for that right-hand rule. Your thumb goes in the direction of the current because the current is the way the electrons are moving. Sorry, the positive charge is moving. And your fingers go in the direction of the magnetic field, and your palm shows you the force goes straight out. So we have two right-hand rules where you keep your hand flat. When you keep your hand flat, fingers always magnetic field, thumb's always velocity, palm's always force. More than one magnetic field line, pitch right with the electrons. And when you're pushing on something, you don't push with your fingers because you'd probably hurt them a lot. When you push a big refrigerator, you push with your palms. So you can think of force, palms. The other kind of right-hand rule we had was when we have one straight thing and one curvy thing. And remember, when we have a straight thing and a curvy thing, your thumb is always the straight thing and your fingers are all the curvy thing. Sometimes that straight thing is current, sometimes it's magnetic field, but the straight one is always your thumb and the curvy one is always your fingers. And we'll go over that right-hand rule a bunch of times, so don't worry if you don't quite get it, we will get it. Snack time! I bet everyone can guess what the snack is going to be based on the ingredients that are right here. Anyone that's had a mother, you know who you are, has had ants on a log. And this week's theme, magnetism theme for snacks, is going to be snacks that my mom made for me when I was a kid. She was really into healthy food, so that peanut butter right there, Laura Scudder's, only has peanuts and a tiny bit of salt in it. And the problem with that kind of peanut butter, it tastes great, I love it, but the problem with it is that it separates. So it gets that oily on the top. I don't know if you've ever had it, but you got to be really careful mixing it up. I spilled oil all over when I was here this time. But then I remembered that to do it, you should take your knife and put it straight in and use it like a mixer first to get the oil going before so it doesn't spill all over the place. But in any case, you get ants on a log. Delicious. Crispy. Satisfying. With that tiny hint of sugar to make it wonderful. Thanks, Mom. That's really good. Okay. So, now we're going to talk about some applications, some simple applications. We'll get to more complicated ones in a second. But some simple applications of some of those force things. The first one is called loop O current. And loop O current says if we have an external magnetic field, and I'm going to say it's all around this. I don't want to draw too much because I'm going to put a bunch of things on there. But so it's all over there, and we have current going through this loop. We can put a battery on it or whatever makes the current. But we want to know what's going to happen to that current. And there's a little hint here. It says find the direction of spin. It turns out that on the top and on the bottom, my theta is either going to be 180 or 0, in which case, either one, the sign of that is 0. So I get no force on the top and no force on the bottom. And I only get force on the side. And so when I do my right-hand rule, I take my fingers that way, my palm, my thumb goes down, and my force goes into the page on this side, and out of the page on this side, which makes the whole thing spin, right? So yeah, so it comes that way and this way. So it's counterclockwise from above, if we're looking at it. And that action of spinning when there's a current in a magnetic field is what creates every magnetic electric motor that exists. So what you do is you take and you attach this to an axle and you put some wheels on it, and that's your electric car. And so because that motor is so simple, that's why electric cars are very efficient, because there's not a lot of moving parts in there. And notice that they're not really actually touching, they're just going through a magnetic field, so there's not a lot of friction. It's a very, very efficient motor, very good for moving these around. There are some problems, and we'll talk about those in class. But every motor, and actually every generator, and we'll talk about that in a couple of times, looks just like that. Loop of current. Another one AP likes, maybe even more than the loop of current, is having two wires next to each other, either, in this case, with the currents both going in the same direction, or them going in opposite directions. Because what this does is it makes you do both equations. You use the first current here to find the magnetic field, then you put that magnetic field into the BIL equation underneath it, and then you can find the force, and in case of an infinite one, which this is, force per length is going to be these things together. Both currents, mu sub naught and 2 pi r, and that tells you what the force is. To get the direction, you find the magnetic field from the first one, which gives you into the page all the way up and down this wire. You can take your fingers into the page, take your thumb up, and your force will show you that it goes this way. If you did the exact same thing for the other one, it would go exactly opposite. The force brings them together, same amount, because if you did it the other way, you just have I2, I1, but everything else would be identical. You get a force together when they're the same direction, and if you ever flipped one of them, they'd be opposite, and we'll show you that right now. What we did this time is straighten them out and then put the two currents opposite and flatten them. So the dark blue things are the direction of the magnetic field from this one out of the page over here and into the page over there. And so where the light blue thing is, the magnetic field is going into the page, and then you take your thumb and go down, and the force shows you it goes out. Use your right hand rule again and find this being the force. If you did it the other way with the light blue one first, put your fingers in, put your thumb up on your right hand, you get a force going that way. So when they're going in opposite directions, your forces are out. But all those equations we did before are identical. You find that B equals mu sub naught I over 2 pi r, and then plug that B in for B and BIL, and you get your force. The last simple-ish application of magnetic force is back to the first thing we did. When we had a particle that was in a magnetic field, it's got a velocity going that way, the magnetic field is going into the page, we can find the force with our right-hand rule. When we do that, fingers go in, but our palm goes up, and our force, let's get a different color for that, our force goes that way. Now force is the same direction as magnetic field, as acceleration. So in the next couple seconds, our particle is going to be right here, and its velocity is now going to be in that direction because it's been accelerated upwards a little. It started at this velocity, so it's up that way. If we did our right-hand rule again and found the new force would be in that direction, which would then make a velocity that was going this way and a force that was going this way. Oops, force, let's get that red. Force would go that way. And if you notice what's happening here, this is now starting to look a lot like a circle. What ends up happening is because the force is always at 90 degrees to the velocity and it's always going the same direction and curving, I get a nice circle when I hit a particle that's in a magnetic field. And the velocity is exactly at 90 degrees. And so I can set QVB, which is my force on the charged particle, equal to mv squared over r, and I can find the radius of that circle in terms of my other variables. If we have a situation where our magnetic field is going up and our velocity has a component going up, that's our v, a component going up and a component going up, I'm not dotting, and a component going the same at 90 degrees, this part will make it go in a circle, this part will make it continue to go straight up. Why is it not drawing? And what happens is it makes a helix going upwards while it's making a circle. And so if you have portions of it in each, maybe I'll be able to make a better picture for that in class. Always a helix if some of it is not at 90 degrees, because that part continues to go upwards while it's going in a circle. This is a picture of the actual magnetic field around our planet. This magnetic field saves us from all the charged particles from the sun. They think that the only reason there's life on our planet is because of this magnetic field. So when we're studying this magnetic field, we need to appreciate it and all that it has done for us. Notice, half of it matches my hair. You should listen to the magnetic fields. They're good. Yeah, evil twin. Maybe it exists.